All right, guys. Good evening. Thanks for joining. Thanks, Tanisha, Pranav, and Sai. So, I hope I'm audible. So, let me check my recordings once. Okay. So, today what we will do is we will quickly go through what we discussed in this overall course, and I also uh, taken down a simple hints important formulas, which is essential for us to understand uh, the key takeaways of our course. Okay. Um, before we start, do you guys have any questions you wanted to ask? Or we can go ahead with the revision. All right. I think everyone is silent. Okay. Anyway, so what we will do is we'll quickly go through the revision, maybe in another 30 minutes or 40 minutes. And then if you have any questions, we can revisit. I also have few questions. I think Tanisha asked and few more people asked. Uh, I think Pranav asked what is Yelstar. So for that, I have a certain explanations which we will see uh, at the end of this revision. And also what we will do is, if you have any questions, if you want to revisit any concepts, we can revisit after this. Okay. So on that note, uh, let's uh, let's revise the whole course. I will do it as much as possible. Uh, so this is just a short note which I made when I first gone through the course. The key takeaways of this course. So those things I made it. So that's what I'm sharing it today with you guys. Okay, and uh, yeah. So basically, it touches each and every concepts that we studied in the uh, okay. So it basically touches each and every concepts that we studied, and what are the main uh, uh, you know important thing that we should remember for each and every concept, right? So that is the what is the gist of each and every concept that we studied and how we are going to apply is what this whole revision will focus on. And at the end of the day, what you will also know is there are few important formulas which should be coming on top of your head. Okay. And that should be helpful while solving your problems. Okay, that those are the two um, important what do you call aim of this exercise. Okay, so we know that we initially started our course with some chapter called motion in space. So uh, the motion in space means not that it's like it's in the upper space, it's like any space. Okay, how the motion happens. So if a body is moving uh, in a space, in a 3D three-dimensional space, what are the certain um, important laws it follows, and how we can well understand it. So that is what we studied in our first chapter. You can call it chapter or week one content, right? So there we studied about motion in space, and we saw few laws. And in this case, since our course is related to rocket propulsion, so we saw something like Kepler's law of planetary motion. So the Kepler's actually stated three laws of planetary motion, and those three laws is law of ellipses, equal areas, and the law of harmonies. So a law of ellipses we already know. It tells about the planet is going to revolve around the sun in an elliptical orbit, right? And law of equal areas is nothing but equal areas are swept at equal intervals of time. So the planet, when the planet moves in orbit, the area swept by the planet will be equal if the delta t time intervals are equal. So that is what the law of equal areas is. And also we know there is something called law of harmonies, which is basically the time period of revolution of a planet, of if any two planet around the sun is nothing but uh, is related to its average distance from the sun, basically. And the dependence would be some 3 by 2, or we know that law, so we can go and revisit. So basically we started with these Kepler's law of planetary motion. By the way, you can stop me at any time, and if you have any questions, you can ask. Okay, so I will continue. So we started with Kepler's law of planetary motion, and then what we did, if there is some body moving in a space, what are the important parameters that we should consider in order to describe its motion? So that was the next thing, right? So if the body is moving, so I want to describe that it is moving. So then, what are the important parameters I should know, right? And those parameters are nothing but velocity, momentum, and acceleration. Basically, we know what are these. And also we studied something called impulse. Impulse is nothing but the change of momentum, and force is nothing but rate of change of momentum. That is the difference between impulse and force. So uh, the change of momentum is called impulse, and the rate at which this momentum is changed is going to be dictated by the force. Okay, the rate. So how much force you apply is actually going to change this momentum of a body, right? And what we this is actually an important concept. Basically, we don't really give uh, much importance to it. When you want to change a momentum of a motion, when you want to change a momentum of a body in motion, you will apply some force, but that force will not be some newtons. So we usually calculate in our physics problems that it will be so this much newtons. If you apply, the momentum is going to change from this to this, or you will go from zero velocity to this much velocity. But the force is not really this one number like 20 newtons or 10 newtons. It is going to vary across a time period, and the one number you say is nothing but average force that you apply to the motion, uh, to the body. Okay, so that is something you should keep in mind. Even though with just a force you can since we are interested in initial point and the final point, I'm interested in initially it is zero, and finally what is the velocity I'm interested in. So if that is the case, you just need to know one number, which is average force that you apply. Okay, and but if you want to know the dynamics of how it changes, you should know the entire time history of the force. Okay, and this is actually true for any rocket. Okay, and this is actually true if you are doing dynamical analysis for your rocket engine or for your rocket motor. Okay, so we will touch upon this more, but basically you should keep this in mind. The force we apply is not just some number of forces, it is actually varying with respect to time. Okay, and then we all know Newton's law of motion, and the important thing here is Newton's second law. Force is nothing but rate of change of momentum, and we always say force is nothing but rate of change of momentum. Here we do not say mass into acceleration here, because the rocket we have here uh, continuously loses mass as it climbs up, right? So that's why the mass is also within the uh, time derivative. Okay, and Newton's second law, actually we don't write it as F is equal to ma, instead we write it as d by dt of mv. Okay, and similarly we also learned Newton's law of gravitation, and Newton's law of gravitation is for two point masses. Okay, and it is basically a two body problem, assuming that there are only two bodies, and only those two bodies are having gravitational pull with each other. So that is one of the assumptions that we have with Newton's law of gravitation. Actually you can extend it for I mean, Newton's law of gravitation is universal, but this formula that we have here is for two bodies. Actually you can extend this Newton's law of gravitation for n bodies, and it soon become a chaotic system, and you may need to restrict yourself with numerical methods to solve the problem and get your results. Okay, um, but for our analysis, since we are launching rockets and we are interested in satellite revolving around the Earth, if that is the case, uh, we are fine with the gravitational pull from Earth, that gravitational pull between the Earth and the satellite, or Earth and the rocket. Okay, so that's why it is easier to get a first order estimate using this gravitational Newton's law of gravitation. Okay, which basically says that uh, the gravitational pull is going to depend on m1 m2 and uh, by r square, the difference, the distance between these two masses. And what you can do is, if you take it for an earth, you just change it with me, okay, and then change r also as re, and then you will end up having this acceleration due to gravity as gme by re. Similarly, you can actually do this acceleration due to gravity for any planet, any moons in the solar system, or anywhere, any celestial body, okay. And the force is nothing but, if you, so since this part is going to be your, um, so this g is nothing but h only if h is very less than re. So basically only at the surface of the earth. If it is nearby, if the h is like, let's say, 10-20 meters, that is very insignificant compared to the radius of the earth. So only near the surface of the earth you can define something called g, okay. And you can directly put, you can ignore this h, and then you can change this to a g, basically acceleration due to gravity. So basically you will have f is equal to mg, which usually we use in our physics, right, undergrad physics. So, since the rocket is going to climb from the surface to the atmosphere, to the orbit, the altitude is going to be comparable to the radius of the Earth. Radius of Earth is around 6,000 kilometers, and altitude will be like 100, 200, maximum 500,000 kilometers. Also, geostationary is around, I guess it's around 20,000 kilometers, basically, I guess. So there, what you have is, the altitude is comparable to RE, so you will no more be able to do this approximation. So that is something you should keep in mind. Okay, so we did this Newton's law of gravitation, and then what we did, we defined something called orbits. The orbits are something, the station, you can call it as a stable pathways around the Earth, in which you can put a satellite with a certain velocity, it will keep on revolving around in that orbit. And uh, you no need any fuel. Ideally speaking, you don't need any fuel if you put it in a, if you insert your satellite into orbit. The reason is the gravity is going to take care of the orbit, basically. So when you put a satellite, you will not put it at rest. You will give some initial velocity, and that initial velocity, the velocity with which, so let's say this is the body which is in uh, orbit. So this is the Earth. Let's say this is a bigger Earth, and the body is in orbit. Now, the body experiences the gravitational pull, and the body is also, you have given some velocity to the body initially. So when you put a satellite in a rocket, the rocket is going to climb up to a certain orbit, and it is going to inject it with certain velocity, right? So that velocity, if you calculate its centripetal component, it is going to be m omega square r. And basically this force, gravitational pull, and the centripetal force balances each other, which is what is creating, which makes this orbit to be in continuous state of motion. So it will not, um, so it's basically coming from the Newton's first law. So if the net force is zero, then you will not have any disturbances in your motion, right? But ideally it doesn't happen, because this gravity will not be same at each and every location in your orbit. It is going to be keep on changing. uh, there is something called J2 perturbations, okay. You can search about this. It's a very interesting concept. So the gravity would be keep on changing, and because of that the orbit height also will be keep on changing, and the velocities will not be more accurate. And so what happens, after a certain amount of time, it will keep on either the orbital height, the altitude will be keep on reducing, or it will be increasing, which we don't want. We want that satellite to stay in that orbit, so we do altitude corrections and attitude corrections to make it stable in the orbit. And that's why we have some amount of thrusters in the satellite, and also fuels in the satellite. And basically there we use monopropellant rockets, which we studied recently in 2-3 weeks back, okay. So anyway, coming back to orbits, or if you are in a stable orbit, which means that you have a gravitational pull and you have a centripetal component, which is going to get balanced with each other. And if this is the case, then you can easily find out what should be your orbital velocity, the velocity with which it uh, you know uh, revolves around the earth. You can rearrange this like this. So this will be your orbital velocity, and this is the velocity you should give. Is the velocity with which you should inject the satellite in an orbit. Okay, and also you can find the time period of this satellite. Okay, so these are some important something you can get it just by uh, equating these two forces, basically force balance. Okay, now the question is, we need this orbit. So what is the energy we need to give to reach this orbit, right? So we said that if you want to go to an orbit, you have to. So initially, satellite will be at rest in the surface of the Earth or in the lab, and then now you want to take that satellite to a certain altitude, and we also told that this at this altitude I should not be at rest. It should move with a certain velocity, which is orbital velocity, which means I am doing some work to put this satellite to an orbit. So what is that amount of work? What is that energy I am putting it in order to reach that orbit is what this thing we are telling. So as I said, we need to reach an orbit from the lab. So there's going to be some potential energy you need to spend to reach that orbit, and also to stay in that orbit you need some kinetic energy, right? And the kinetic energy to stay in the orbit is simple, which is mv naught square by 2. But the potential energy, your height is keep on changing, and while your height is changing, the distance between the um, satellite and the earth is keep on changing, right? So since we said that uh, uh, the gravitational force is nothing but Re plus H, which means your potential energy will be keep on changing as you go up. So that's why we do this integration from Re to Re plus H. Okay, because we have a dependence of radius square in the denominator. Okay, so when we do this integration, this is the total amount of energy. This part is potential energy, this part is kinetic energy. This is the total amount of energy we require, and if we integrate this part, and then if we simplify this, you will get something like this. And then what we did was, this is the total amount of energy required. Now uh, what is the velocity requirement? We actually talk about delta v in terms of doing this. So um, the velocity requirement is nothing but whatever the energy you get is the amount of energy you require in order to accelerate an object of that mass m from 0 to some certain velocity. If you want to move that to a certain velocity, what is the amount of energy you need to spend is same as this energy required to put a mass in the orbit. So basically it's for a convenience that we change this. Instead of telling in terms of energy, instead of telling in terms of joules, we tell in terms of velocity. What is the delta v I require? From delta v you can easily find out the energy. So basically delta v square or vt square by 2 times the mass of the satellite will give you the amount of energy. Okay, so instead of talking in terms of energy required, we talk in terms of delta v. So these two are nothing but interchangeable. Okay, so this has nothing to do with what is the velocity with which it has nothing to do with orbital velocity or any other velocity. It's just we are trying to uh, quantify energy requirements in terms of velocity. Okay, that's why we use delta v here, and we do it only in the rocket propulsions just for the sake of convenience. Instead of dealing with megajoules and these big things, it's easier to do in terms of vt. There are also other benefits. I will let you explore about it. Okay, so this is about the delta v, which is nothing but the energy required to put a certain mass of satellite or mass of anything into an orbit, in a certain orbit at an altitude of height h. Okay, and then we understood certain concept called escape velocity. this escape velocity is nothing but I wanted to escape from this gravitational field of Earth. If that is the case, what should be my uh, uh, energy required? Okay, so that energy also we are trying to calculate in terms of escape velocity. So that energy is nothing but just the potential energy. So you need to reach from you don't want to reach an orbit, you want to escape from here. So then what you do, you just uh, your height becomes very high, so that's why you integrate from re to infinity. I want to go to infinity. At infinity I will not have much of a gravitational force. So if that is the case, what is my escape velocity is, this is the escape velocity. Okay, so this is the velocity. Let's say if you are at rest and if I'm just pushing you with certain velocity, then if I push you with this escape velocity, you will certainly escape the Earth's atmosphere. Okay, or basically Earth's gravitational field. Okay, so these are few um, planetary mechanics, celestial mechanics that we try to understand. It's very minimal information actually, but this is enough for us to do our rocket propulsion analysis. Okay, so basically what we did was initially, so the course itself is actually designed in such a way that first you should understand why we need rocket propulsion. And if you know why we need rocket propulsion, now we will tell you what are the steps to achieve that target. So the target is you want to go to space, you want to go out somewhere, and that target you should be able to define it properly, and that's why we actually studied all these concepts. What is the energy we require, what is the orbital velocity, what are the things we are interested in. We are interested in putting a satellite, and for that what is the energy and what is the velocity uh, we need, or so we are trying to understand it in that way. And once we understood that, okay, I have to reach this, and if I want to reach this I need to give some force, and that force, that energy, I have to give it through some means, by some means, and that is going to be from a rocket. Okay, so basically that rocket is going to give me is the power source to achieve this dream. Okay, and if rocket is the power source, then I should focus on how to improve my power source, and or what are the different classifications I have about my power source. So if rocket is the power source, what are the important parameters I should consider? So that is what we studied. And then if, okay, rocket is will be something like it will have nozzle, chamber, and things like that, tanks and all those stuffs. And uh, if I need if I want to achieve this much thrust and this much ISV, then I need to do something with the nozzle, and then I need to do something with the combustion chamber, and then uh, I need to do something with the tanks and the if it's a liquid propellant, I need to do with that. If it is solid propellant, then I need to do some optimization in that. So you see, this is the structure of this course. This is how it has been designed. First you should understand what is the aim and how are we achieving that aim is what is being taught later. And to achieve that aim, what are the important things you should understand is what been taught in the subsequent chapters. Okay, so and then we ventured into theory of rocket propulsion. So we understood that we need some delta v, and that delta v is going to be provided by this rocket. Okay, and um this delta V is actually the basic energy requirements that we talked about, and this is something coming from the design or mission. This is coming from the mission. Okay, so let's say if you want to go to a lower Earth orbit, you have certain delta V. So something, I guess it's around like 8,000 kilometers per second. Okay, this is the delta V to go to lower Earth orbit. If you want to go to moon, I think it's around like 14,300 kilometers per second. If you want to go to Mars, then you will have certain kilometers per second. So this is the amount of energy you need to give, or this is the amount of acceleration you have to give if the body is at zero velocity. Okay, so if that is the case, we actually studied a famous equation called Tsiolkovsky equation, right? It's actually from a Russian, mathematics teacher, I guess. He's a mathematics or physics teacher. I think mathematics teacher. So he actually initially proposed this equation, and it's a famous equation. We use it till now actually. So he told that I hope everyone must have gone through the derivation. So I'm not showing you the derivations here. I'm just showing you important formulas. So this delta v is nothing but the jet velocity times natural log of mi by mf, where mi is the initial mass and mf is the final mass. Okay, and you can also write in terms of mass ratio, and where the initial mass is, let's say if you have a rocket, there are three components. One is propellant, you have another, you have payload, which is a useful mass, which is what I wanted to put it in the orbit, and then additionally you have this structural mass, which is not going to contribute to anything, but it is required for the operation of rocket. So one is propellant, which is going to get emptied at the end of the mission. Another is structure, which is going to stay there from right from the beginning to end, and the another is useful payload, which is our interest, right, which is of our interest. So the initial mass is going to have all these three masses, but the final mass will not have propellant because propellant has been exhausted, it has been spent. And based on that we define these ratios. I'm not going into details. uh, and then you can use this to find out, let's say if I want to put a useful mass, payload mass of this much, and then this ms can be written in terms of beta, which also you can, there is some this also you can actually uh, it comes with the technology basically. So at this current technology point, probably it is around 0.03. When I say technology, it's nothing but the material development. Basically it has to withstand that much high pressure and aerodynamic loads, and it has so includes this electrical components, how simplified. So as the technology goes, this we can always go with the better materials and improve the performance by reducing these structural components. So that's why I say this beta is you can quantify in terms of technology level. Okay, and then you, let's say you can find the mass of propellant if you know all this. Okay, so let's say you know this and you know this, and then assume the jet velocity and you want to go to a orbit of 500 kilometer, then you can find out what is the mass of propellant I need. So that is some important parameter, right? So that is the usefulness of this, whole equation. Okay, it basically gives you an idea of the masses that we are dealing with in terms of rocket. Okay, and then we define something called propulsive efficiency. This is basically due to that when the rocket moves, the gases are coming out with certain velocity, and um because it is coming out with certain velocity, if that velocity is greater than or greater than the vehicle speed, then you have certain amount of velocity which we are losing. Okay, which we are losing to the atmosphere. If by chance if we use it, then our performance of our engine is going to improve. So basically, since vj is greater than v vehicle speed, the gases are coming out with higher velocity, and we were not able to use those for our uh, for the propulsion. Basically we are losing some energy for the propulsion, so that's why we actually quantify that in terms of propulsive efficiency. Okay, and the propulsive efficiency will be one only when velocity of the uh, rocket is equal to the jet velocity. That might happen somewhere in your whole uh, mission. Okay, whole climbing. All right, so those are some important parameters, and then comes the performance parameter, which we dealt with this for like every week of this course, every assignment we have to, come and revisit this again and again. So these are the performance parameters, the important performance parameters. Basically, these two are more important than the impulse. So impulse is nothing but the mass of propellant times the Vj, velocity of the propellant. Um, and the specific impulse is nothing but impulse by mass of propellant, you can say, or F by mp, you can say. Well, specific impulse equal to Vj is true under certain conditions. I hope you guys can uh, remember this. So Specific impulse is going to be nothing but the thrust divided by mass flow rate of the propellant. Okay, it is kind of like a, mileage. uh, so same like mileage for your car, this is kind of like a mileage for your rocket. Okay, and thrust is nothing but we know m dot b into jet velocity. And then there are few more things, impulse to mass ratio or thrust to mass ratio, that is to give an idea of how efficient your rocket is, because certain rockets will have very high thrust to mass ratio, which means with a lower amount of mass they can produce that much thrust. And if that is the case, then you can put a very heavier payload into orbit, or you can go to a very high orbit with a less amount of propellant mass basically. Okay, so that is also one of the ratio, which this we don't use that much in this course. But if you're designing, or if you're proposing a new variety of rocket, then they will ask for this, how better is this compared to whatever present rocket we have, right? So that is about the performance parameters. We will be keep on revisiting this again and again, and you can expect a bunch of questions from this performance parameters also. Okay, and then we also did a minor comment on staging of rockets. So basically, with one stage, if you want to achieve a certain orbit, it's going to take enormous amount of propellant mass. We already did that exercise, right? So that's why we do it in stages. Okay, so for the first stage, the useful mass will be the whole thing above. Okay, and for the second stage, the useful mass will be whole thing on top of it. Okay, or you can say for the first stage, the final mass is this thing, and the initial mass will be this plus the first stage. Okay, so that will also be useful in calculating the delta v, how the delta v is defined. And then we also did something called clustering of rockets. So usually what we do is with one engine here may not give enough thrust. Okay, here actually we are dividing the delta v, where during staging what we do, we divide the delta v's. So we are giving each stage will achieve this much delta v. Let's say if I have 8,000 kilometers per second as my delta v, now each stage is going to give me a delta v of 4,000 kilometers per second. So the first stage is delta v will be just 4,000 kilometers per second. Second stage will take the other 4,000. So we actually divide the delta v's. But in clustering, what we divide is we divide the thrust. So basically, in the same stage, we will have number of rockets. If you see the Starship rocket, you will understand there will be like lot of Raptor engines. Um, like 29 to 30 Raptor engines you have. So each and every engine is going to produce thrust, and let's say you need 200 newtons. Each and every engine is going to provide you, collectively 200 newtons. So that is what the difference between staging and clustering. We divide the delta V requirements. Here we divide the uh, thrust between these rockets. Okay, that's a minor comment. Anyway, and then we have rocket nozzle and performance. Uh, so basically, we understood that I need a rocket and it should produce this much thrust to put a satellite into orbit, and also its performance is defined by ISP. Now, if I want to produce this much thrust, what are the things? What should I do with the rocket? How should I design the rocket? Right, and the first part it comes is nozzle. Okay, and in the nozzle we applied uh, compressible flow theory. Basically, isentropic we apply. uh, those are those are few assumptions you should remember. This whatever we did in this course is like we assume that it's an isentropic flow. Okay, um, which you can assume to a certain extent. It is also true to if you use this isentropic flow theory, and you're able to predict things, and that will be closer to, let's say, 90-95% closer to the reality. Okay, so um, yeah, anyway, this will be the nozzle, and in the nozzle what happens is you are just doing uh, the 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 pressure here would be high, the pressure here would be low, and basically it will be ambient pressure initially, and here the pressure will be high. We will see why the pressure is high or temperature is high, but basically the pressure is high. There is a pressure gradient which drives the flow, so flow is going to go through the nozzle. Now, while it is going through the nozzle, the temperature here is high, which is a thermal energy. While it is going through the nozzle, it is going through a constriction. It has going through a, the areas keep on reducing, which means as per mass conservation, what should happen? The velocity here should be more than whatever the velocity is present here. So velocity should keep on increasing along the nozzle, because we at least it should keep on increasing until the until area is restricting because of mass conservation, right? But what happens at a certain point, the velocity will keep on reducing, and velocity will be keep on increasing, and at certain point it reaches Mach number equal to 1. Okay, what does it mean Mach number equal to 1? The speed of sound is also equal to the velocity of the. So why does that, why is it important, right? So how does the speed of sound is affecting anything happening in the mass conservation, right? So mass has to be conserved as it goes through the nozzle, but at a certain point in the throat, the velocity of the flow is equal to the speed of sound, which means the speed of sound is nothing but the rate at which the disturbances in the flow can travel, or rate at which the information can travel within the flow. Okay, let's say if I change something here in the exit, it will travel at the velocity of speed of sound c. Now, and also if I change something here, it will also travel with the speed of sound c. Now, since I am also traveling with speed of sound c, v is equal to c, the uh, information will never reach me, right? Because information will come at c and I will be traveling at equal to c. The velocity here is c. So it will not have an idea that it is, well, the contour is expanding after the throat. So it will be keep on getting accelerated as you go down. So this phenomena, we call it as this phenomena, actually we call it as a supersonic flow um, in the converging diverging nozzle, and there will be always Mach number equal to 1 at the throat. Okay, and what you will have is, you will have the Mach number will be, it will be subsonic in the inlet, and then it becomes supersonic, which means velocity will be more than the speed of sound in the divergent portion of the nozzle. And what also happens is, because of the information doesn't reach the flow, doesn't reach the fluid, it will never know. Even if you increase the pressure, if you increase the pressure, what happens? The pressure gradient across the nozzle changes, right? So pz, if I, let's say I have 1 bar here, or let's say 1 megapascal here, and I have 1 bar here, at that time it has choked here. Okay, now if I increase it to 2 megapascal, the information reaching here will not be, the information will be reaching, but the flow will not know this. So because of that, what happens? Whatever the mass flow rate will get fixed. Okay, the mass flow rate of the nozzle will get fixed. Okay, so for a given pc by pe, you will have choked mass flow rate, m dot choked, and you cannot increase your mass flow rate above that. Okay, and that is something you should remember. But if pc by pe itself increases, then the mass flow rate, choked mass flow rate, keeps on increasing. Okay, so let's say I'm fixing the pe, and I keep on increase the pc, then at that time you will have mass flow rate, your mass flow rate keeps on increasing. But by any chance, if you say that pc by pe is same, pc by pe is, let's say, 10, but my pc was 10 megapascal and pe was 10 bar, and I'm going to increase from this, if I increase it to 100 megapascal, and this if I increase it to 1 megapascal, that is not changing the pc by pe, right? And that will not lead you to increase in the mass flow rate. So basically, if the pressure ratio doesn't increase, then you will not have increase in mass flow rate, you have the choke mass flow rate. That is the maximum mass flow rate you can achieve in the nozzle. Okay, that is something you should remember. Anyway, so we already studied it, like you can revisit it again. Now what is our point of interest? Our point of interest is to get this vj, right? Because this vj is going to define my thrust, and thrust is what is good. Thrust is already defined by the mission. So mission is going to tell me how much amount of thrust I need, and that thrust is going to given by the rocket. So for that, I need to know the exit velocity and mass flow rate. And the exit velocity we are actually calculating using this relation, which basically coming from the mass conservation. Okay, basically coming from the mass conservation, we know how. And after substituting lot of relations, isentropic flows, adiabatic conditions, all those things, once you substitute this, you will get all these things. And yeah, this is basically compressible flow theory. Anyway, now how do I increase this jet velocity? Because I want to have a very high performance rocket, and I need to have very high, I want high thrust, so those things are important to me. If I want to increase this velocity at the exit, then the way is to increase the temperature, chamber temperature, and also to decrease the molecular weight. So those are the two things. One is increasing the chamber temperature, either increase the chamber temperature or decrease the molecular weight. The reason is, if you increase the chamber temperature, you have high energy inlet, you have energy, high energy, then you can convert it into a very high kinetic energy. Okay, you have high thermal energy, you can convert to a very high kinetic energy. So basically, if you increase the Tc, you have high thermal energy. But what is the deal with molecular weight of the gases? If I reduce the molecular weight of the gases become more and more lighter. And if it becomes more and more lighter, it's easy to accelerate in the nozzle, right? So because it has become weight, the molecular weight has keep on reduced. With the same amount of action, the same amount of delta P, I can accelerate to a higher velocity. That's why the molecular weight of gases coming into picture. And it is also true that if you change the gradient, pressure gradient, if you increase the pressure gradient, you are going to have higher mass flow rate, and which is going to lead to higher uh, thrust, and here higher jet velocity also. Okay, and then so we also need to know the, if you want defining, by defining a CD nozzle, then you need to know its expansion ratio. So the expansion ratio is going to be dependent on this pressure ratios, which we have a formula. And then we also uh, did over expanded, under expanded nozzles. So that is because basically the velocity with which air comes out will be at P exit, but that will not really match the atmospheric pressure. Okay, the P exit is the velocity with which airflow comes out or gas comes out. That pressure will not be equal to the atmospheric pressure. Okay, atmospheric pressure is something from outside. So when that those things are not equal, then you will have this kind of over expanded and under expanded nozzles. And then we also did what are the different performance losses you can have it in a nozzle. We also studied the flow separation it happens, and also this side thrust, you since the streamlines are not straight, it's going to go through like this. Streamlines will be like this. What happens is, some of the thrust is nothing but the horizontal component. In this place, it's nothing but the horizontal component. But you, since your flow comes out in a slightly different direction, there you have a vertical component here also, which we call it as side thrust, which is not contributing in any way. Okay, and that is why actually people do not use conical nozzle. Instead, they use this contour nozzle. So contour nozzle will look something like this. So which it actually tries to streamline it at the exit, so that you will try to take most of the uh, you know uh, energy as possible. Okay, and then you have performance loss, flow separations we did, and then contour and conical nozzle we studied what are the differences. And then we came to an important parameter, it's a characteristic velocity. Okay, this is the characteristic velocity is actually you know gives you a idea of how efficient is your combustion chamber is. The reason is, this characteristic velocity, even though we define it in terms of PC, AT, and M dot, basically it doesn't depend on PC and M dot. Okay, please understand that C star doesn't depend on PC and M dot. It actually depends on temperature of the chamber and molecular weight of the gases. Okay, so but there will always be losses, and you can get this formula from here. So you can actually, actual C star would be something like this, and the theoretical C star would be something like this. So you can always find an efficiency. This is the efficiency of C star efficiency for the system you can find out. Okay, but the C star is going to depend on temperature of your combustion products and the molecular weight of your combustion products. Okay, that is what it is dependent on. And then, so basically this C star is, since it deals with combustion temperature and molecular weight, it is basically giving you an idea of the performance of the um, you know combustion chamber. Okay, you can say it's giving us a performance of the combustion chamber. Now, we know that performance of the rocket is nothing but ISP. So basically rocket has two main components: combustion chamber and the nozzle. So performance of the combustion chamber is given by C star, and there should be some performance parameter given by the nozzle, which is nothing but CF, thrust coefficient, or CT or CF, whatever we call it. And multiplying this C star and CF is basically your ISP. So you are actually dividing the performance of rocket into two things. One is C star, one is CF. And C star gives an idea of combustion happening, and CF gives an idea of this expansion. How much amount of multiplication you are doing to a certain uh, flow stream. Okay, so the amount of thrust generated by the flow stream, how much multiplication you are doing because of putting a nozzle, a divergent part of the nozzle, is what this CF is going to give us. Okay, so basically it's nothing but thrust generated divided by chamber pressure into AT. And you have this big expression which we all know how it came. And then basically ISP is nothing but C star and CF. Okay, and then now that we studied more about nozzle, now it's time to go to one step further and study. Okay, nozzle requires some thermal energy. Now let's see how we can generate that thermal energy. So basically in this course we mainly focused on converting a chemical energy to a thermal energy. Okay, so the chemical energy is coming from burning the chemical propellants within the combustion chamber. So that is the chemical propellants we studied, um, and how are we burning it, and how are we getting the temperature, chamber temperature, basically. Okay, so we define something called mixture ratio, which would be useful in calculating this. Mixture ratio is nothing but mass of oxidizer divided by mass of fuel. We know if I want to burn something, I should have a oxidizer, I should also have a fuel, right? So uh, this fuel will react with oxidizer, and it is going to give me the combustion products, and it's going to liberate energy, and it will reach a higher temperature. And that is what you see here. Then for that we defined a parameter called heat of combustion. So uh, the important concept here is these fuels and oxidizers will have certain energy in it, in form of chemical energy. Okay, which you cannot sense it. Okay, and we call it as a formation enthalpy or formation energy. Okay, so it's the formation energy which is stored within the chemical compound, as as part of, let's say, bonds. Okay, let's say you have a petrol or diesel. It's a hydrocarbon chain, right? And each and every carbon atoms are bounded by double bond or single bond, however it is. And all these energies are stored in terms of bonds. And if you are able to break these bonds, you can get those energies out. So that is what literally we are doing in a chemical reaction. Basically you have a petrol, which is a very big hydrocarbon chain, and you have an oxidizer which is going to bombard on these, and then it's going to break the bond, and then take the carbon outside and forms a CO2. That is exactly happens in a chemical reaction. So which means the energy is coming from the chemical bonds. Okay, that is, the energy is coming from the formation enthalpy. And that's why we defined a term called heat of combustion, which is nothing but formation enthalpy of products minus formation enthalpy of reactants, where reactants is the propellant. So formation enthalpy of reactants should be higher than the formation enthalpy of products. Then only we'll get net gain, heat, net energy out, right? Only if the energy of the reactant is higher than the product, we'll get a net energy. So that is what we defined here, heat of combustion. And then we have, let's say, if this is the reaction, this is how you define a heat of combustion to be. And then but heat of combustion is not really useful. We are interested in temperature. So because the thermal energy at the inlet to the nozzle is, we are worried about the temperature. What is the temperature of the gases? If I want it as high as possible, then only I can have higher jet velocity. So to find the temperature, what we basically have to do is we have to do energy balance. Initially, before combustion, I have certain energy, and after combustion, I have certain energy, and both the energy has to be equal. So, but that energy is not just formation energy; it also contains the sensible part. So it has some formation enthalpy, and then it has some sensible enthalpy. Uh, the formation enthalpy of reactants would be higher, and sensible enthalpy of reactants would be lower. Now, in the product side, this things gets opposite. So formation enthalpy reduces, and whatever the formation enthalpy difference was, it gets added as a sensible enthalpy. Sensible enthalpy is something we feel, and we measure it using a temperature. So that's why your temperature of the gases goes up. Okay, but enthalpy of total enthalpy of both reactants and the products will remain same because energy has to be conserved, right? So total enthalpy includes both formation and sensible enthalpy. So it's just a change of, you know, form of enthalpy from one form to other form. It's what happens in the combustion, and because of that you will have a higher temperature, and you find that using this formula. Okay, there are different ways of finding it. I've shown you two ways during our uh, classes. Anyway, just to revise. And then the criteria for selection is going to be the heat release. So any propellant, which propellant should I select? It is going to be based on the heat release, or the amount of heat release I'm going to get. It's going to get what is the molecular mass of the product, because that is affecting the uh, you know uh, the performance, the C star and jet velocity, and then storability, density, or other aspects which we have to have it. And then we entered, okay, these are the propellants, these are chemical reactions happening, and there are two ways it can happen. One, either you can use solid propellant rocket or you can use liquid propellant rocket. And in the solid propellant rocket, it is going to burn based on APM. So basically burning rate is you can it's this is how they measure it. So for different pressures they measure the burning rate, and they will plot it, and for each and every propellant they will give you this is the burning rate. You can use it and in your rocket, and you can do your analysis, or you can design your rocket based on this. Okay, and this is nothing but a simple energy balance near the combustion zone of the propellant, which I'm going to skip. I think it's fairly straightforward. Basically, the combustion. So initially, the solid propellant has to melt, evaporate, it comes out, and then what it has to do, it has to go through a flame. It combusts here, and then while combustion, it reaches very high temperature. Basically, very high temperature, and because it reaches very high temperature, there will be heat conduction coming, and that heat is actually used to, melt few more solid propellant. Okay, this is a kind of like a cycle, so it's a self-sustaining cycle. This is how actually solid propellant burns in the rocket motor. And for that we did energy balance, we did mass balance. And the important thing we should know is when you create a solid propellant, there are some mechanical properties you need to take care. And the mechanical properties of the grain you need to be careful with, because if the grain breaks somewhere, or if the grain has a crack, what happens is you're increasing the surface area, and if the surface area increases, the uh, uh, the flame is going to spread through there, and it is going to start generating more and more gases. More gases increases the pressure, and increasing pressure again increases the burning rate. Increasing burning rate again generates more gases. It's a positive feedback loop, and the pressure will be shooting up to a very high value, and that's why your rocket burst in the mid-air if there is some cracks in your grain. So mechanical properties of your grain is also important. Okay, and then there is this steady state operation. The What we say is whatever is generated in the propellant is going to be equal to the mass flow rate through the nozzle. So when we equate these two, we will end up having this relation, and you can actually find the chamber pressure, how it is going to vary as a function of burning surface area. If the burning surface area is increases, then pressure is going to increase, and how it is going to vary is going to depend on all these parameters. And then during the initial transients, what happens, that also we studied. We also introduced some parameter called L star, which we will visit again at the end of this session. Now uh, this parameter n, this has to be uh, it has to be less than 1 in order to have a stable uh, you know, operation because of the play between mass flow rate and the mass flow rate of the generation mass flow rate, or the propellant burning, what do you call it? Mass flow rate of the propellant, and the mass flow rate of the nozzle. Those two are, related in a different based on here. So that's why it has to be, less than one in order to have a stable operation. Okay, and then we did something called ignition burnout, erosive burning, and then propellant grains. You have progressive, regressive, and neutral propellant grains. You have like, what do you call this? Cylindrical grain, star grain, and all these things we will be getting. Okay. Will we get recording of this lecture? Yeah, you will get it by the end of this class. Okay, and then you have propellant rockets, liquid propellant rockets. In this liquid propellant rocket, what we have is we have this. Till now, it's a solid propellant. You cast it and put it inside. In liquid propellant, you have a tank, you have liquid supply, and it has to be pumped because you need a higher pressure in the chamber. That's why you have a pump, and if you have a pump, you need to give a power source to it, and that is given by the turbine. And if you have a turbine, you need to run the turbine using some gases that you are taking uh, from your working fluid itself. So we did different cycles. We see what are the different ways you can do the same thing. And yeah, important thing is we wanted to, from designing perspective, we wanted to know how the pump, what is the power of the pump, what is the injector design. All those things are very important, and that is what we did. So the power of the pump is going to depend on only the delta P we are interested in. So this will be at lower pressure. The pressure in which you want to inject is going to be at higher. So that pressure difference is provided by the pump, and based on the pressure difference is the amount of work you require for the pump is going to vary, and also based on the volume flow rate. And yeah, for turbine it is going to be the temperature difference. Okay, basically that is what. And then we had some non-dimensional parameter for the pumps and all those stuff. Otherwise both are same, solid propellant and liquid propellant. In terms of finding the performance, everything is same. Only thing is liquid propellant, it will have an injector, and gap fluid and oxidizer comes in, and then it forms a sheet of propellant layer, and it forms uh, droplets, and the droplet starts burn. Okay, and in solid you will just cast it and put it inside, and solid will be keep on burn. That's it. And then you have monopropellants that we studied, in which you have hydrazine, and then there is this catalyst bed which is going to improve your uh, reactions. That's why you have it. And then there is something called hybrid rocket also. What you have is you have a solid propellant, solid fuel, which itself will not burn. In general, in normal solid propellant rocket, you will have fuel and oxidizer mixed together as a one grain, and they will put it inside. Here only fuel grain will be there, and then you need to spray oxidizer on top of it in order for it to react, and then gases will generate it and go out. That's a different way of uh, hybrid rockets. And also we slightly touched about combustion instability, right? So basically, as we said, if there is a crack in the solid propellant, this is what happens. Similarly, if there is a uh, small place where the pressure is little bit high inside a liquid propellant rocket, then mass flow rate reduces, right? Because the injector delta P will be reducing, so mass flow rate through the injector will reduce. And if the mass flow rate reduces, your thrust reduces, so pressure reduces. And if the pressure reduces, mass flow rate again comes, will increase. If the mass flow rate increases, then the pressure increases. The pressure increases, the injector mass flow rate again reduces. So this is like a cycle keep on going on, and sometimes it might increase its amplitude, and it might go to again it will burst, or it might uh, you know you know deteriorate. That also it can happen, but that is the combustion instability people are studying. There are acoustic instability also people do within a combustion chamber. Okay. And then there are a few advanced rocket propulsion technology, which is electrical propulsion, nuclear propulsion. We did. The problem with electrical propulsion is even though you will have a very high ISP than the chemical propellant, your thrust will be very low. The thrust of chemical propellant is very high compared to the thrust of the electrical propulsion. That is the reason you have uh, that is the reason they don't use it for launch vehicles. So launch vehicles you cannot use electrical propulsion. Nuclear propulsion people wanted to use, but it has its own problems. If there is a if it blasts, then nuclear reactor will be everywhere, surrounding you, and it's going to affect you, right? Nuclear radiation, people are afraid of nuclear radiation. A lot of safety issues are there in terms of nuclear propulsion. Okay, and then we have solar sails and pulse detonation engines, totally advanced concept. It's just we just introduced it so that you can read it on your own. Okay, so this is what basically we covered in this course. um, uh, we we started from what is our aim, and then we try to build the rocket by component wise, from nozzle, combustion chamber, and then as a rocket as a whole system, solid propellant and liquid propellant, and then few advanced propulsion concepts also we study. Any questions you guys have? You wanted to do you want to if you have any questions you can ask.
Sir, in staging of rocket,
Mm-hmm.
the payload mass for the first rocket will be the summation of the structural mass of second and third stage.
Actually, it will be total mass. The second stage will also have propellant. So for the first stage, the payload mass would be the total mass of the second stage and the payload.
So that means structural plus propellant plus payload.
Right.
Main.
For the so structure and propellant of a second stage plus the third stage. Let's say third stage is the payload, then payload mass of the third stage, or let's say there are only two stages, and you have a payload. Then for the first stage, the payload for the first stage would be the total mass on top of it. It is going to be structural mass of the second stage, payload mass of the second stage, and also the propellant mass of the second stage. All three will be the payload for the first stage, basically. All right. All right. If there are no questions, I wanted to briefly talk about this L star. Probably in the last class, I think Pranav or someone asked, "What is this characteristic
Yes,
length?"
yes.
Okay. What is this
Yeah.
characteristics length, and why it is useful, right? So actually, it turns out to be it is a important parameter for designing. I also realized it later. It is not just some random variable that they use it, basically. So this is like a characteristic. So characteristic length is this uh, you know chamber volume. For, let's say, we talk about the liquid propellant. Okay, liquid propellant, it makes more sense in the chamber volume divided by the throat area. Okay, that is the characteristic length. The reason is the chamber volume is actually uh, defined by, so what is going to define your chamber volume? How will you select a chamber volume, right? So that is the question. So if you are designing a liquid propellant rocket, within that volume I want my combustion to be complete. Okay, only if my combustion is complete I will have a higher temperature, and then I'm going to have a higher performance. If the combustion is incomplete, then I will have lower temperature, I'm going to have a low performance losses. So this chamber volume has to be what you call uh, designed in such a way that your combustion is complete within the chamber. So that's why this chamber volume is going to be a function of your, let's say if you have a liquid propellant, you will form droplets, and the droplet is going to vaporize. It has to vaporize. Okay, so the vaporization rate, it has to, once it vaporizes, it has to mix with fuel and oxidizer. So there is some mixing time related with it, and also it has to go through combustion. So once it mixes with fuel and oxidizer, it has to go through a combustion. So there's kinetic rates of the chemical reaction. So all these vaporization, mixing and combustion has to happen within this chamber, which means you need to design your rocket in such a way that all these three things happen within your combustion chamber. So That is why your chamber volume design is going to depend on all these three things. And actually you can, these three things are actually coupled. So while evaporation, once it evaporate, it comes out, the fuel and the oxidizer will come out, and then it starts reacting and it puts a flame here. This is how ideally actually happens within the liquid propellant rocket. There will be a droplet, and above that there will be a flame. So actually all these three things are coupled to each other. Okay. And actually you can say something called residence time, or the combustion. Basically you can say it's a residence time. There is, you want to happen, you wanted to make sure that all these three things are happening within this residence time. Okay, how do you find this residence time? So the residence time is nothing but what is the amount of time your propellant is residing within your combustion chamber. Okay. And so let's say it enters the combustion chamber at one part at the injector, and it takes like 1 seconds to reach the nozzle end. Okay, then the residence time is nothing but 1 second, and within that 1 second you have to complete your combustion. Okay. And so basically, to have a complete combustion, then what happens? You can write this VC, chamber volume. If it complete, if you want it to be completely combusted, then you can write it as m dot into TR by rho. Okay. So this residence time is nothing but equal to, you can write this to be equal to the total time scale. So you can write this as evaporation rate, mixing time scale, plus the kinetic time scale or chemical time scale. This is the total time scale of your entire physics, combustion physics happening within the chamber, and you want your propellant mass to stay within the chamber for this entire time scale. And if you want that, then for a complete combustion, you can replace this chamber volume in terms of mass flow rate times the, or volume flow rate times the uh, you know residence time. That will give you this kind of expression. And but this at and m dot are actually related to each other. So basically this L star is actually a function of residence time, or this combustion time. Okay. So this will be a function of only residence time, which means that residence time is going to depend on the rate at which I am evaporating, which means it is going to depend on the injector diameter is going to be, so injector is what is generating droplets, because it will uh, injector is not generating droplet, but the flow of injector and how it is interacting with how the two jets are interacting is what is breaking up the droplets and coming. So it's going to be a function of injector. The mixing and the mixture ratio is going to be a function of mixture ratio, and the combustion is going to be a function of mixture ratio and propellant. So basically, for a given propellant, mixture ratio, and the injector designs and all the other parameters, you will have an L star. Okay, they have defined an L star basically. It has nothing to do with physical length, but they have defined an L star. Once you know the L star, uh, based on your uh, you know rocket calculations, you must, for a this is a designing problem, right? So for a given design you need a certain thrust, and for a given thrust you will fix the area of the throat will fix the mass flow rate. Okay. uh, or the other way, so thrust will fix the mass flow rate, and the mass flow rate will fix the area of the throat. So if you know the area of the throat, and if you know the propellant you are using on the mixture ratio, uh, the corresponding L star you can choose, and you can directly go and tell that this will be my you know uh, chamber volume. Okay. So this is basically used for designing the combustion chamber. They have already did these mapping, this propellant mixture ratio and injectors mapping to the L star, because this is going to depend on the residence time, and the L star is just a function of residence time. So they already did this mapping, and for any thrust you need, or any engine you are going to design, you just choose a propellant. Okay. And then you get its L star, and based on the mission you choose a AT, and once you know L star and AT, you can find what would be the volume of your chip. That is why this characteristic length is actually useful. Okay. And few important things you can understand about this characteristic length is, if the characteristic length is high, then what happens, your chamber volume increases. if the chamber volume increases, your weight is also increases, so which is going to cause you poor performance. Okay. And what is also true is, if the chamber volume increases, the surface area of the volume also going to increase, right? And if the surface area increases, the heat loss to the surroundings also going to increase. So there will be thermal losses. Because of that, the chamber temperature reduces, and if the chamber temperature reduces, there's going to be poor performance. Okay. And there is also other problem, there is going to be a lot of frictional losses within the chamber, because you will have a higher, bigger, uh, chamber volume. And increasing the chamber volume also reduces the pressure within the chamber, and if the chamber pressure reduces, it will produce lower thrust, which is again is not good. So you need to have as low L star as possible. And usually the L star is around like 0.75 for most of the liquid propellants, and if you are able to get like 0.5 or zero point 0.4, it's pretty well. Okay. So that is basically the use of L star. Is that clear? uh,
Yes, yes, sir.
okay, so basically it's for designing. And in this course we didn't go that much, because it's a introductory level course. But if you take a, let's say, design of rocket engine book, let's say for example, uh, there is one book by, I think, AIAA. There is some educational series book. Okay. They release a lot of books. Basically, in that, one of the book talks about this design of liquid propellant rocket engines, or design of liquid rocket engines, I guess. So you can look into it. Okay.
Do you know the author? Who's the author?
uh I don't exactly remember the author. um um so yeah, so if I know, I will let you know. Maybe I will write it here, and then, yeah, I will just write it here. Okay. While I upload, I will just write it.
You're saying that it's an AIAA, right?
Right. AIAA is
AIAA.
a publishing society.
Okay, okay, okay. I'll search that.
Yeah. But anyway, I will give a reference also here. You can check that. It's an interesting book. You can find a lot of books like that. Okay. Um, and then I also have a few more things, but before that, Shruti ma'am was raising. Uh, do you have any
Yes, sir.
questions? Okay.
Sir, could you please explain residence time once again? I
Okay. Yeah.
missed it.
So basically, residence time is nothing but the amount of time the propellant stays within the chamber. That's it. So if the chamber has to, so let's say there is some mass of propellant entering. So some mass of propellant entering with some velocity v. Okay. Now it enters the chamber. Okay, and the chamber length is, let's say, some meters. Let's say, let me put some number. Let's say I have 1 meters per second, and the chamber length is 1 meter. Okay. Now the mass with which the propellant enters, it is going to go through this, and it is going to exit at this point. And the time it enters would be 0, and the time it leaves would be, basically, since it moves at 1 meters per second, since it's had to travel 1 meters, then it would be like 1 second it will take to reach the other side, right? So this time, the time spent by the propellant within the chamber, is basically the residence time. Okay. And this residence time is important, because this residence time is something you have it in your hand. Basically, the reason is, you are going to design your chamber length, and also the radius, right? So basically, our diameter, and basically you will be defining the chamber volume. Okay. You are going to design this chamber, combustion chamber, which means you have residence time in your hand. Now you have to select your residence time in such a way that all these three all these three parameters, or all the combustion physics happening, should happen uh, within your residence time. So that is why this is also an important parameter. Is that clear what I'm trying to say?
Yes, sir, understood.
Okay.
Thank you.
All right. So yeah, that is about L star and the residence time. And then we have Tanisha was asking about this breakdown voltage. Actually, it was nothing but uh, that's a minimal voltage you require in order to form an arc. The reason you have a certain limit is uh, for any voltage it will not form a arc because there is always be a resistance, so it will act as an insulator. That's what it turns out to be it's a straightforward concept in electrical, so we are mechanical, we didn't understand it that time. But so it is like a minimum voltage for which the insulator electrically breaks down and becomes conductive. So if you have an insulator and if you apply a voltage difference across it, since it's an insulator, it should not allow the current through it. And but if you put a very high voltage at a certain voltage, what happens, because the insulator is also in material, right? So at a certain voltage difference or at a certain potential difference, it's the insulator breakdown in the sense electrically it breakdowns and becomes conductive, so it starts passing few some amount of current in it. And that is what the breakdown voltage is. Here what we are doing is we are assuming this air gap as an insulator. So you have this arc jet and you have the cathode and you have the anode, and from cathode to anode you need to form an arc, and you have a separation, there is a air gap between these two, air or any gases, and you have certain pressure also there. So this difference will actually this gap will actually act as an insulator. And once you apply certain voltage, certain breakdown voltage, after which it starts forming the arc. Okay, so this gap will be act as an insulator, and after a certain voltage it forms in arc. So that's why they are correlating, like they are equating these two and telling that it's a breakdown voltage, minimum voltage, which is going to be which we require in order to establish an arc. And only if you establish arc, you will heat up the gases coming, and only if you heat up the gases, you will get any performance, right? So that is the thing. This is something for your information. I just took it from Wikipedia. You can also this is just it just tells that it is this breakdown voltage is a function of pressure and the gap distance basically. That is this basically, I think uh, they did the experiments and then they took it, they tried to you know fit this equation into it. So it is not coming basically from the first principles. So from experiments they found out that it's a function of pressure and uh, distance between this cathode and anode, which is what the breakdown. So in that way they are trying to equate it with the breakdown, because that is what we will be able to manipulate. The gap and the pressure will be able to manipulate. So that is how this Bastian's law they come into picture, and that is how they get the breakdown voltage. Okay, is that clear, or was this the question you wanted to ask, why we need a minimal voltage or something else? Did I?
No, sir, it's clear.
Okay, thanks, Tanisha. And then I actually revisited the um, lecture and I understood what professor was telling about static and dynamic model. Uh, so it's basically I took an example here to show. Professor was taking very big example, but I will try to give you a gist of with a simple example. So we studied this solid propellant rocket, right? In that solid propellant rocket, we let's say I wanted to find the chamber pressure, how the chamber pressure varies within the combustion chamber of the solid propellant rocket. Now let's say, for example, if I know the rate at which the area is regressing, let's say for example if I know that, then you can actually find chamber pressure in two ways. Okay, so one is, there is this formula, you just substitute it. Okay, problem solved. And if you substitute it and if you plot it, what happens is, let's say if I want to plot it with respect to temperature, see, the SB is a function of temperature, the rate at which this propellant is regressing is a function of time. So if this is the function of time, then pressure also, for each and every time you can find the pressure. So what happens is it will look something like this. Okay, this is the kind of, you can say it's a static model, telling that you are not interested in how the dynamics of the system varies. I just have an equation. I will just apply some value to find out what would be the pressure at each and every thing. When you come into a dynamic model, you try to understand its time evolution, how it is with respect, it is basically time dependent, how the pressure is really varying with respect to time. Okay, that is what the dynamic analysis usually deals with. It will be with respect to a time. So the same pressure profile you can actually get from this analysis. Basically this equation, if you remember, it's nothing but the mass conservation again. um, Basically if you have the combustion chamber, if you have this solid propellant rocket, um, the change in mass of the rocket dm by dt is equal to the mass of propellant minus the mass of mass flow rate through the nozzle, right? Because so dm by dt of the change in mass of the rocket, change in mass of the propellant in the combustion chamber is equal to m dot of propellant, this is the rate at which propellant burns comes out, minus the propellant rate at which the propellant leaves through the nozzle. Okay, this is a function of like c star and blah blah blah, and m dot of propellant is nothing but rho propellant, rb, and all those things. So if you substitute these rb and sb, okay, if you substitute, if you just do this here, you will get this pressure equation, and you can see that pressure is a function of time. And let's say you solve this equation, see, you solving in the sense you can actually analytically you can solve, but you have this pressure p power n dependence here, and also you have p dependence here, and in addition to it you need to have an initial condition. Please remember that you need to have an initial condition. P at t naught is equal to some p naught you should have, and then using this initial condition and this ode, if you solve it, let's say in MATLAB, or let's say you can solve it by your own using RK4, if you integrate it, what happens is you will get a temperature, pressure profile with respect to time. Okay, and that profile will start at p naught, it goes up and then goes up, and once the propellant is over it comes back to the same p naught again. P naught is nothing but p ambient, let's say. So this whole entire time history you will be able to get based on the dynamic model, and this dynamic model is more closer to the reality. This is just gives you an idea that this could be the pressure, right? This could be the pressure. It doesn't know the history, what has happened before, what is going to happen. It doesn't know anything in the static model. But in dynamic model you are actually integrating with respect to time. So you from the initial condition, so you can get the entire time evolution of the pressure, how it is going to be, while you can still have the, let's say if you are interested in what is the peak chamber pressure I have, this will also give you, for let's say 40 megapascal is your peak pressure. This can also predict the 40 megapascal. Here also the maximum it will reach also will be around like 40 megapascal. Okay, it may not be same, but it will be same only. It will be around, even though the static model can predict better in the whole scheme of things. Like if you want to have a entire variation of chamber pressure, you need to have a dynamic model in order to capture it. And one additional thing is, since you know the dynamics, this is the way. So this equation is nothing but the dynamics equation, or you can say this is how the pressure is going to vary with respect to time is defined by this equation, which means you know the dynamics how it is going to vary. Now if you want to control, you can integrate a control system to it. Of course solid propellant rockets cannot be controlled, so there is no point in integrating. So in for a liquid propellant you can have a dp by dt, which is going to be a function of mass flow rate of oxidizer and fuel within the you know combustion chamber, which can be controlled using a valve. Okay, so if you know this relation, you can use this as an dynamical system, dynamical model. You integrate it with your control system, you put a control, let's say this is what I need to maintain the pressure as. If the pressure goes high, reduce the mass flow, if the pressure goes low, increase the mass flow rate. All those control system analysis you can do only if the model is dynamic. So that is the reason you have this dynamical system. Okay, this is just a simple example in order to show you that this is what a basic difference between dynamics. The more control systems and all we will include, that is what professor was explaining you in the lecture. So, is this clear? I think Shruti asked the
Yes,
question.
sir.
Okay, all right. So, yeah. So, if you have any questions related to your assignments, if you want, you can ask. That is all I have today. I hope this revision would be helpful for you. If you don't have any questions, we can call it a day. Um, Thanks for joining, by the way.
Thank you, sir.
All right. Thank you, Kanisha.
Thank you, sir.
Thank
Thank
you.
you very much.
Thank you, sir.
Thank you. So anyway, I will be staying here for maybe around like next couple of minutes if you want to ask. Or yeah, well, maybe I think Akhileshwar and others one they want the revision to be on Saturday. So probably what we will do is maybe if you guys also have time, if you guys have any questions, you can again come on Saturday, this Saturday. Okay. So I will be anyway revising the same thing again. So you no need to attend if you since you have attended now, you no need to attend maybe in the first hour or so. Uh, and if you have questions regarding how to solve, then you can come and ask. I will be happy to answer. Okay, coming Saturday. If not, also it's fine. All the best for your exams. Maybe we'll meet in some other course. All right. Uh, Thanks, Tanisha.
Sir, I have one question for the exam.
Okay.
Like we have the numerical problems, right?
Hmm.
Which we need to solve with pen and paper.
Correct. Yeah.
And we have to enter the answer in the system.
Correct.
So can we do the rough work? Is it allowed? Because I'm giving remote proctored exam.
Mm-hmm.
Uh, so can I use pen and paper for solving the problems, or will it is it accepted or not?
So basically, usually it should be accepted, I feel. But what I would suggest is I would request you to mail to NPTEL and ask about this because I'm not aware of how this is happening and how we are going to do it. They will be
Okay,
the right person to answer this question. So
sure, sir.
whether it will
Okay,
be accepted or not. If it's a remote proctored, then they will be keep on monitoring you, I guess. So
yeah,
okay, I think yeah. Please raise this question to the NPTEL team. They will be able to answer it better.
sure, sir. Okay, thank you.
Thank you.